Okay, I'll share my screen. Give me a moment. Yep, can you see my screen?
Yes, please.
All right. So what we're going to do today is we're going to elaborate a bit more on what we did previously, which was the naive base, and we're going to take a particular case in point, which is sentiment analysis. So what we're going to do is we're going to take a specific problem and try to solve that problem using the naive Bayes algorithm. Um, of course, before solving the problem, we'll also develop some mathematics that will help us solve the problem. Okay. So here goes the problem. Give me a moment. Let me make it a little bigger. All right. So here we go. Um, you have a bunch of documents. I'm calling it document. It might look like a sentence or a phrase to you, but I'm just calling it a document. So imagine each row to be a document. All right. So in this particular case, these are movie reviews, basically. Somebody said just plain boring. Another document suggests entirely predictable and lacks energy. The third one is no surprises and very few laughs. The fourth one is very powerful. The fifth one is the most fun film of the summer. So these are, imagine each row to be a document. And then, of course, technically, you'll have a lot more sentences in the document, but for the sake of discussion, we'll just assume a bunch of words to be a document. A cat is essentially a category. We're basically categorizing these documents based on sentiment. So of course, we're talking of supervised learning. So which means each of these documents is tagged to a particular sentiment. Evidently, the first three documents would be tagged to a negative sentiment. The last two documents are tagged to a positive sentiment. Now the question is, given a document, can we predict a sentiment? So here is the test document. And this is the test document, predictable with no fun. That's the test document. The question is, can we predict what is the sentiment associated with this document? Okay, I'm using the word document again and again because technically it can be a bunch of paragraphs. But for the sake of keeping it simple, what you're seeing here is a simple phrase. Uh, it's not even a complete sentence, but the principles are the same. It's not going to change. You're going to apply the same principles for, be it a paragraph or be it, a short sentence or even a phrase. The concept remains the same. All right. Now, so what would be our plan of attack? We have to think about three key problems here. What is a document? That's number one. Can we represent a document as a set of features? And the question is, what are those features? That's problem number one. Problem number two, how many classes are there in this problem? What are the target classes and how many are there? And problem number three, how do we determine the class to which we assign a document? Basically, how do we learn the association between a document and a class? And how do we formulate this mathematically? Because finally, it's all about mathematics. All right. Point number two is easy to answer. I want somebody to tell me how many classes are there in this problem? Two,
Two
evidently.
positive or negative.
One positive, one negative. So that's evident. Okay. Of course, now we'll have to start thinking about what is a document? How do we represent that as a set of features? What are those features, etc.? That's something that we'll have to dig deep to understand. And the final thing is we'll have to formulate the whole thing in a in a mathematical sense. That's of course something that we would do in a short while. Okay. So the concept, the way to understand this problem is we formulate this as what is called as, this is regarding, by the way, how do you interpret a document? Okay. This is if you look at the plan of attack, the first one is we'll have to interpret what a document is. So this is how we interpret a document. It's called a bag of words. So just imagine to the left, you see a review. You put all those words into a bag, all right? And against each word, you ascertain the frequency of occurrence, okay? So, I mean, just imagine, let us say there are some 10 positive reviews given by people, all right? And you put all those positive reviews in a bag. Something like loved, amazing, would pop up very frequently, isn't it? Right? A word like sucks would not pop up, if the reviews were to be positive. Likewise, if the reviews were to be negative, you take 10 reviews and put that into a bag, and then figure out the frequency of occurrence of these words, then the word say sucks might come up very frequently if the reviews are bad, right? So the way to understand a document is a text document. We're dealing with text documents here, so which means we're not dealing with alphanumerics and stuff like that. So a text document is treated as a bag of words. Each word may occur at different frequencies in the document, okay? Evidently, you can have 1 occurrence, 10 occurrence. Now just think about this question. Does the order of the words matter? By order, I mean, let's say you look at the word love. Would it matter to us from a sentiment standpoint? Would it matter if the word love occurs at the first, let's say you have a sentence and the word love occurs at the start of the sentence? That's one say review. Let's say there's another review where the word love occurs at the end of the sentence. Would you differentiate between the first review and the second review, or would you treat them as similar? What is your take?
Depends on how you use love, right? If you use it as noun, you can create a different sentence, then the meaning itself will be different. But
No,
if
forget
you're
semantics. Forget semantics. That's semantics.
No, it doesn't matter because
It
we are
doesn't.
taking the frequency of the word present in the paragraph.
No, no.
right?
See, Yash is also throwing a very interesting problem, which is what is called as semantics, because the same word has different meanings in different sentences and all that. So Yash, we are not doing semantics here. That's very deep. Okay.
But
So
if
assuming
Yash
that
is
we don't know the
referring,
semantics of how
it's
the word is
positive.
used,
Like
so
if you use it in a review, then it means that you really like it, or like it's positive.
exactly. So in a very trivial sense, I'm trivializing it. There's no semantics here. There's no wordplay here. I'm not introducing all that, because the same word in a different context can mean anything else. You could have used the word even sarcastically. That is also possible, right? Kudarkama Vande, you might say something, right? That's possible. So I'm not bringing all that to the picture, but in a very trivial way, I wouldn't care whether the word love in a typical sentiment analysis, especially say movie reviews, for instance, I wouldn't care if the word love popped up at the start of the sentence, or the word love popped up, say, at the end of the sentence. It wouldn't really matter to me, right? Now the next question is, what are the features of the document? Each individual word is a feature. Each individual word is a feature. Okay. So hence, sorry, I'll change this. A document can be interpreted as a collection of words, not okay. And of course, we know how many classes are there in our problem statement. There are only 2 classes. All right, positive and negative. Okay. Now, this is a bit involved. So just follow me carefully, okay? To the left, of course, what we have is the each row is a document. The document is assigned to a sentiment, negative and positive. What are we trying to figure out? We're trying to figure out the sentiment associated with the document, which goes by predictable with no fun. Okay. So we're trying to figure out the sentiment associated with that document. Okay. So what are we trying to do? Given a document, we are trying to ascertain the class. Right? That's what we're trying to do. I give you a document. In this case, the document is somebody's review. What is the algorithm supposed to do? The algorithm is supposed to determine the class, whether it's a positive class or a negative class in this case. Okay, positive means it's positive sentiment, negative means it's negative sentiment here. All right. Now let's probe further. So I'm going to read this. Given a test document D, out of all classes, think of C as a list of all classes. In this case, we just have 2 classes, right? We're looking to figure out the class C hat. Don't worry too much about the algebra, but we're trying to determine the class that satisfies the following expression. Okay. This is the expression. Forget the arg max. Let's just look at this probability. Forget everything else. Just look at the probability P of C given D. What does it mean? What does P of C given D mean? Forget everything else, folks.
Probability of the category which should be falling, either it's positive or negative, given the document, the words in the document.
Exactly. So P of C given D means C is, of course, the class. D is the document. So given the document, what is the probability that it belongs to a particular class? All right. That's what P of C given D means. Now, question is, in this context, how many classes are there?
2.
So which means given a document, how many probabilities will I try to calculate?
2.
What would I do? I will try to calculate probability of negative given D, probability of positive given D, right? Let's say I've done that calculation. How we're going to do that calculation is something that we'll come to in a short while. But let's say we've done that calculation. What do we do with that then? How do I decide the class to which I'm supposed to assign this document? Let's say I've done that, calculated the probabilities.
The probability of which class is higher, the class is assigned to the.
Exactly. So if say probability of negative given the document is say 0.3 and the probability of positive given the document is 0.7, evidently I'll assign the document to the positive class. Okay. So this whole expression arg max basically means that it says what it does is it maximizes this P of C given D. It figures out the case where it's maximum, and whatever is the argument here is basically the class here. So don't worry too much about what exactly this means. It's not a concern, but effectively what we're trying to say here is, look, I'm going to calculate P of C given D for all classes. In this case, there are 2 classes, and figure out the one where the probability is maximum. So if probability of negative sentiment given the document is maximum, then I would say I would assign the document to negative sentiment. Alternatively, if the probability of positive sentiment given the document is maximum, I'll assign the document to positive sentiment. It's as simple as that. All right. Now let's probe this further. Again, don't worry too much about argmax. C given C belongs to C. Don't worry too much. It's just nomenclature, folks. Our concern is P of C given D. Okay, that's the probability that we're going to figure out. Can somebody tell me, not Abhinav, someone else, how did this LHS become RHS here? So why is P of C given D is equal to whatever, this whole expression? Forget the argmax bit. I'm talking about the stuff related to probability. How did that happen?
Equated base.
Like probability of C given D. Probability of C given D is probability of C intersection D by probability of D.
Okay.
And then probability of C intersection D is nothing but probability of D intersection C,
Okay.
which is nothing but D given C into probability of C.
Okay. One moment. Give me a moment. Are you able to see my screen? A blank screen? Can you?
Yes, yes.
All right. Fine.
Whiteboard.
Yes. Yes. It's a whiteboard. Sorry. I'm using this for the first time. So give me a moment, folks. So let's say probability of, I'm struggling with this, sorry, C given D, sorry, excuse me. I'll just try. I need to get used to this. Give me a moment. Otherwise, probably probability. No, it's not. Sorry, folks. Thought it was working well. Give me a moment. No, it doesn't work that well. It's okay, no problem. Sometime later. Okay, let's do this. So probability of C given D, right? So I'll just do it on Excel. So this is simple stuff. Probability of C given D is equal to, what does Bayes theorem suggest? Don't you? I think by this time we should all understand the formulation of Bayes theorem. C given D given C multiplied by probability of C divided by, sorry, I don't know why this keeps happening with Excel. Probability of D. All right. So that's basically a Bayes theorem, right? I hope you guys are comfortable with this formulation. This basically comes from Bayes theorem. All right. What Mugundan did was he derived this using this expression where he said, look, this is actually probability of CD divided by probability of D. And then he expanded this into this. Probability of CD can be written as D given C multiplied by probability of C. All right. So that's what this is. So no rocket science there. This is just Bayes theorem. All right. Now, question. I'm going to calculate this for two classes, correct? I'm going to calculate this for two classes. This whole probability expression, I'm going to calculate for two classes, the negative class and the positive class. My question is, does the denominator matter? Do I need to calculate P of D?
No,
Why?
because we need to just compare. So whether it is
Exactly,
positive or negative.
exactly. So if you look at this, I'm going to do this for two classes, right? So basically, what will I do? I will compute. I'll give it another shot. Let's see if the whiteboard works again. I have a stylus, but I don't know. Yeah, I think it's much better. So C given D, well, it struggles.
This you're doing something like there's a toggle between the arrow and pen
Sorry,
in the bottom. You
sorry,
have a
Sharon?
toolbar, right? You have a toolbar, right? When you're
Right.
writing, it toggles between the pen and the arrow. So
So
I think you should not click there must be a button.
where in the
Stylus.
stylus is it? Okay, I think I get it. Okay, let me try. So let's look at this expression. Minus, no, Yash. I'm not clicking on that at all. Wait, so probability of, no, and then probability of positive given it's nope, not pointless. I need to get used to this. Apologies, folks. Go back to Excel. Okay, so probability of negative given D and then probability of positive given D. This is what we're going to do, right? And we're going to figure out which one is greater. This is greater or the other one is greater, right? Now, the point is in both cases, in the denominator, you'll have P of D, correct? Because when you apply Bayes theorem to this and Bayes theorem to this, P of D will be there in both cases. So our objective is just to figure out which one is greater, right? Either this is greater or the other one is greater. So in that case, we don't need to compute P of D. All that we need to do is just focus on the numerator. So if you look at, and this is what they're saying here. They're saying, look, don't care about P of D. Just focus on the numerator, which is P of D given C multiplied by P of C. All right. What is P of C? P of C is called as a prior, which means we'll take an example in a short while for you to understand. But P of C basically means, look, I have a bunch of documents, right? What proportion of the documents are positive? What proportion of the documents are negative? And I'm talking of the training. For example, in this case, can you tell me what is P of negative? So we're talking of P of C. So
3 by 5.
3 by 5, correct. And what is P of positive?
2 by 5.
Exactly, correct. So that's there. Then comes the likelihood. The likelihood basically means given C, what is the probability of getting the document? See, we are flipping it. What we want is the other way around, C given D. But of course, what Bayes theorem allows us to do is, given C, you can figure out what is the probability of D. Okay. But then now the challenge is, what the hell is this D? How do I figure out P of D given C? P of C is very easy to determine, right? We've already figured it out. But the challenge here is, how do we figure out P of D given C? Now, the way to do that is, we can express the document. That's what we were talking about here. We're going to express the document as a bag of words, right? And each word is a feature. So if there are 10 words in the document, then there are 10 features. So if you look at it, this whole expression is written as probability. I mean, of course, P of C doesn't change. That remains the same, evidently. But the D has been replaced with F1, F2, F3, Fn given C. Basically, F1, F2, F3, F4 are basically, look at them as features, but features are words here. Okay. I hope you are with me until this point. Now, but there's still another problem. How do I calculate P of F1, F2, F3, Fn given C? That problem still remains, right? So how do we calculate this? Now, that's where we're going to work with certain assumptions. Let me explain what those assumptions are. Okay. The first one is that, the bag of words that we already understand. that we interpret the document as bag of words. That's simple. Okay. And in the bag of words, the position doesn't really matter. So the word love has the same effect on classification, irrespective of where love occurs. It could occur in the, it could occur as the first word in the sentence, or other first word in the document, or it could be the last word in the document. It doesn't really matter. All right. The second important assumption, this is something that we discussed previously. Remember conditional probability, folks? If we are assuming that given a class, F1, F2, F3, Fn are all independent. Okay. Okay, let me explain what it means. And you have to tell me whether it's really, I mean, does that truly reflect reality or not? So let's say we're talking of a positive document, okay? Or rather, a document that has been classified as something with a positive sentiment. F1, F2 are all words. Now, what this is saying is, given the document, carries a positive sentiment, the occurrence of one word does not impact the occurrence of another. So, which means the occurrence of the word love would not impact the occurrence of another word, say superb or exhilarating or fantabulous, something like that. All right. That's the interpretation here. But the question is that true? When you write a positive review, because it's given C, which means we're talking of, say, one particular class of reviews. It's a positive review. Okay. So let's say we are writing a positive review. What this is saying is each of these words are independent. The occurrence of each of these words are independent. They're not dependent. All right. My question for you is, of course, this is the assumption. This is the naive based assumption. But my question for you is that indeed true?
No, miss.
Why?
Like we are just assumed like no semantics is followed, so it is true in this case. If
Exactly. If semantics is followed, typically you would associate a lot of positive words together, isn't it? Right? So when I write a review, I would say it was good, it was fantabulous, it was fantastic. All those words would come together, right? So typically there would be a mild association between these words when you write a positive review. And likewise, when you write a negative review, the word say sucks, and then say it was bad, and then it was horrible. All of them kind of come together. So one can't say with certainty that there is no association between these words, given a class, right? Remember, it's all conditional here. It's given a class. We're talking of how these words are associated. But naive Bayes goes with the assumption that given a class, all these are independent. That's what naive Bayes does. Okay. So what it does is it assumes this expression P of F1, F2, Fn given C is equal to P of F1C into F2, I mean F1 given C into F2 given C into Fn given C. This goes to the basic conditional probability. Remember the independence, conditional independence that we discussed in the previous session, where P of AB. So let me ask this question. Okay, I'm going to ask this question. P of AB given C. If A and B were to be conditionally independent on C, can somebody expand this expression for me? I'm
P
saying
of
A and
A
B.
given C into P of B given C.
That's right. Correct. A given C multiplied by P of B given C. Exactly. This is what we learned in the previous session. And this is called as conditional independence, right? So conditional on C, we're saying A and B are independent. That's precisely what we are doing here. We are saying, look, these are F1, F2 are features, they're words here. And conditional on C, which is some sentiment, either positive or negative, all these features are independent. That's the assumption that naive Bayes makes here. So which means the probability of F1, F2, Fn given C is equal to probability of F1 given C into F2 given C all the way up to Fn given C. Okay, so what we're doing is, if you look at this expression, now we have replaced this bit, this whole bit, with this expression. F1 given C, F2 given C, all the way up to Fn given C. And that is basically expressed as, this whole stuff in the bottom, at the bottom that you get to see here. Okay, this basically means a multiplication symbol, so don't really fret over it. This whole pi-like thing basically means I'm multiplying F given C. All right, but don't worry about it. That it's all notational there. The focus is this expression, P of F1 given C multiplied by F2 given C all the way up to Fn given C. And of course, there is a P of C as well. Okay. Now the final thing we need to do is, I'll come to this. How are we going to calculate P of F given C now? So look at the formula, folks. Here we go. I need this P of C and then this whole thing in the bracket. I've figured out that this stuff, P of F1 comma F2 comma all the way up to Fn given C, is nothing but this nice looking expression where I multiply all these probabilities. So that's something that's already settled. But the question is, how do I figure out P of F1 given C, F2 given C, Fn given C? How do I even figure it out? Right? And that's where we're going to do some very interesting stuff. You're not going to understand this so easily. So let me come up with an example. Okay, so let's do an example. So our focus here, by the way, in this example, is just to calculate. Let me just explain. It's just to calculate this bit, P of F1 given C into F2 given C all the way up to Fn given C. P of C, we understand, it's very easy to calculate. We did that here, right? Probability of negative is 3 by 5. Probability of positive is 2 by 5. So that's very easy. P of C is very, very easy. The challenge is to calculate this F1 given C, F2 given C, Fn given C. Okay. So our focus in this example, does not involve. The complete, okay. So the complete mathematical formulation involves P of positive and P of negative. We're not worried about it. Okay. So don't worry about it. Our focus, as I said, is to calculate F1 given C, F2 given C, so on and so forth. Okay. So let's take an example here. Positive sentiment. So that's AC. These are the features, which is a bunch of words. Love, exhilarating, 2 words. The count of love is 3. The count of exhilarating is 4. Evidently, total number of words is 7. No problems there. Okay. Negative sentiment. These are the 2 features, sucks and horrible. The count of sucks is 3. The count of horrible is 2. Total number of words is 5. Okay. Now, this is the text or the document that we wish to, we're going to use this to figure out what sentiment it is associated with. It's a very interesting piece of text. It says, it sucks, but at times exhilarating too. Okay. That is the document. Now, there are some challenges here. Let's start with the first challenge. Now, there is a possibility. Now, Now, how did we get to this? I didn't talk about how we got to this. Basically, you'll have a training set. You'll put that into that bag of words, and then you come up with all this, okay? Now, there is a possibility where, look at this. Look at these words, it, at, times, but. Now, these are words that don't exist anywhere here. You look at this here. I have love, I have exhilarating, I have sucks, I have horrible. I don't have it, I don't have at, I don't have times, I don't have but. Right? So what do we do about them? Typically, we ignore them. Why? Because we can't do anything about them. They don't exist anywhere here for us to determine a probability, correct? So we just ignore them. So let's ignore it, at, times, and but. So can you tell me what am I going to be concerned about in terms of features? So if you look at it, let's go back to this. So here's a document, and I'm converting that into P of F1, F2, F3, Fn given C, correct? Now, can you tell me how many features are we dealing with here? The document is, this is the document here, right? It sucks, but at times exhilarating too. Now, how many features are we dealing with?
2.
2. Why? Because we've excluded all those words, it, at, times, but. We've ignored them because we can't do anything about those words. So we are focusing only on 2 features. What are those features? Anyone?
Sucks and accelerating.
Correct. So sucks and exhilarating. These are the 2 features that we are focusing on. Okay. Now let's look at this. What do we do now? If these are the features, and assuming, remember, conditional independence, I can write this as P of F1 given C, F2 given C, so on and so forth, right? So here we go. I'm going to calculate P of sucks given positive, P of exhilarating given positive, right? I'm going to do that. Now, what is P of sucks given positive?
0.
Okay, why is it 0?
Because the occurrence of sucks in positive is 0. So
There's no occurrence, exactly.
yes.
Sucks doesn't occur. So if you look at the positive sentiment, the word sucks doesn't occur at all. So what is the probability of finding sucks? If the sentiment is positive, there is no occurrence. So it is 0. All right. What is the probability of exhilarating given positive? Just tell me the fraction, folks, not the decimal.
4 by 7.
4 by 7. Absolutely. So now we know that to get this probability of F1, F2 given C, we'll have to multiply the individual probabilities. We know that, correct? Look at this. F1 given C multiplied by F2 given C, so on and so forth. Here, there are only 2 features. So we're going to multiply this and this. Now, since one of them is 0, the product will be 0. Is it clear so far? Now let's do the other one, because we're going to do 2 things here. We're going to figure out positive and negative sentiment, right? So now let's come to the negative one. What is the probability of sucks given negative? Tell me in terms of fraction.
3 by 5.
3 by 5. So look at this. Sucks occurs 3 times. Total number of 3 times. Total number of words was 5. So 3 by 5. What is the probability of exhilarating given negative?
0.
0 again. Why? Because I didn't find the word exhilarating here. Correct? So that's 0. So again, I'm going to multiply probability of sucks given negative, probability of exhilarating given negative. I get 0. You see, I'm stuck. This is a standard problem here. Why? Because this is multiplicative, isn't it? So if, and remember, it is this can occur, right? Because when we are talking of positive sentiment, you would find that we would use only certain words. You will not find those words in the negative bucket at all. Correct? So seeing things like these are very common, but this kind of completely derails the whole algorithm, isn't it? Now, this is where we're going to use a trick. It's called Laplace smoothing. Okay, it's very easy, not too complex, but let me explain what Laplace smoothing here is. What you're doing here is take the entire vocabulary. Okay, take the entire vocabulary of words available here. Tell me how many words are available here. Entire vocabulary. In this case, how many words are available?
4.
4. Yeah, what are those words?
Love, exhilarating, sucks, horrible.
Horrible. Correct. My vocabulary here consists of 4 words. Okay. What Laplace smoothing does is it adds one occurrence of these words by default to both positive sentiment and negative sentiment. By default, it assigns. Okay, so which means, so let's understand this. So here is love. There were 3 occurrences of love, correct? So it assigns another love. It just assigns one occurrence of the vocabulary. Okay. So now tell me how many occurrences of love would be there in positive sentiment?
4.
4. How many occurrences of exhilarating will be there in positive sentiment?
5.
5. How many occurrences of sucks will be there in positive sentiment?
1.
1. How many occurrences of horrible will be there in positive sentiment?
1.
1. All right. This is what it does. So now the total number of words become the sum of all this, which is 11. All right. Likewise, let's go to the negative sentiment. As I said, it assigns one word each from the vocabulary to both classes. Okay. So how many occurrences of sucks in negative sentiment? It assigns one word each from the vocabulary. So how many occurrences of sucks?
4.
Sorry, louder.
4 VC.
4. Okay. Horrible.
3.
Love.
1.
Exhilarating.
Again 1.
1. Exactly. Right. So here you go. 4, 3, 1, 1. Okay. Now what will happen is the number of words in the denominator. Okay. Can you tell me there's a clean pattern here? There was 7 here, 11 here, 5 here, 9 here. What can you tell me what is that pattern? From 7 it goes to 11, right? In the total number of words. So it increases by a certain amount. What is that amount?
4.
Okay.
Number of
course,
features.
is it number of features?
Yeah, these.
Distinct
Or
features
can
into
we say
positive.
exactly? Or can we say the number of words in the vocabulary? Can we say that?
Yes, we see.
Right. So effectively, you can say that the increase is the number of words in the vocabulary. So here, the number of words in the vocabulary is 4. Love, exhilarating, sucks, and horrible. Right. So what you would see is in the denominator, basically, when I say denominator, because when you calculate probability, this is what you're going to do. You'll take a word and then divide it by the total number of words, right? I mean, the frequency divided by the total number of words. So that will increase by the number of words in the vocabulary, okay? Which is what you see here. You know, when they say we here, it's the number of words in the vocabulary, okay? All that is, you know, terminology. The example will help you understand, okay? Now you can comfortably calculate a probability of sucks given positive and probability of exhilarating given positive, right? And then compute this product. Likewise, you can calculate probability of sucks given negative, probability of exhilarating given negative, and you can compute this product, and then you can figure out which one is greater, okay? And then say, look, this particular document will be assigned to such and such class. Okay, that's the whole deal, folks. Now, what we're going to do is, I'm not going to go through this. Whatever I said now is there in this slide. It's just that this is all nomenclature. I mean, there's a lot of symbols and nomenclature. Okay, so don't worry too much about it. You can, as long as you understood that Excel, you're good. So let's solve this problem patiently. Okay. So the math is all set. So let's get cracking. Here is a problem. Training. There are 5 documents. Get a pencil, paper, or Excel ready. Okay, do the calculations. So 5 documents. Here are these. Each of these documents. So we're going to start with some simple stuff. What are we going to calculate? We're going to calculate the following: probability of negative given test. This is what we need to calculate, right? Negative given test and then positive given test. Okay. So we know negative given test is test given negative multiplied by probability of negative divided by probability of test. What is this, folks? How did we get this? How did we get this?
Bayes theorem.
Exactly, it's Bayes theorem. As simple as that. Correct? You don't need to think at all. This is Bayes theorem. Likewise, don't you see that this is also Bayes theorem? All right. Now, before we proceed, we need to determine the number of features. Correct? Look at the test document. How many features are there? Just open your eyes, look at the test document and tell me how many features are. How many features are there?
4.
No, just have a good look, folks. Remember, I talked about a case where certain words may not occur. We ignore them.
2.
Is it 2?
3.
Okay, what are those?
Predictable, no fun.
Okay, what happened to with?
With might be frequent.
Sorry,
in
say that
other
again.
documents too. With might occur in other documents too.
Is that the reason why we neglect with? So remember, for every feature, what are we going to do? We're going to determine the probability of feature given the sentiment, correct? We're going to calculate that. Can I calculate with this data, with this training data, will I be able to calculate probability of with given positive sentiment? Can I?
No.
Can I calculate probability of with given negative sentiment? Can I?
No, it is not possible.
Why?
Because it is not occurring in the vocabulary.
Exactly. The word with doesn't even occur in the training document set, right? If it occurs in one of them, I can add that to the vocabulary, correct? And remember, using Laplace smoothing, I can make sure that I can push that word in both positive and negative training sets. But the word doesn't even occur, which means it's not even part of my vocabulary. It's like saying, look, I've been trained all this while in the English language, and then you introduce this word called Kekran Mekran. How do you even know what Kekran Mekran means? I wouldn't know, right? It's something like that. So that's the reason why we exclude with. So how many features are there? 3 features. What are those features? Predictable, no, and fun. Okay. And that's what you see here. Of course, we go with the assumption that these features are conditionally independent of the classes. So which means I can separate this into 3 multiplicative factors. What are those multiplicative factors? Can somebody tell me? If I say this is conditionally independent of this class. These are features F1, F2, F3. And this, of course, the negative class. I'm saying these features are conditionally independent of the negative class. So how can I, if conditional independence holds true, how can I split this?
Plain predictable given negative,
Okay,
no
into
given negative, a fun given negative. We
exactly.
multiply all three.
I can multiply all three. Okay. Likewise, I can do something similar here. Predictable given positive, no given positive, fun given positive. Multiply all three. All right. Now, so let's start with this. Okay. Let's do the math. P of negative. What is P of negative? How do
3 by
we,
5.
sorry, say that again. 3 by
3
5,
by
correct?
5.
So basically we are saying, look, there are 5 documents. 3 of them are negative. Okay. So P of negative is 3 by 5. Okay. Just make a note, folks, somewhere. P of positive is
2 by 5.
2 by 5. All right. So that's simple. Okay. So we've already figured out. This. We've already figured out this bit. Okay. No problem. And as we discussed before, we don't need to worry about this because this occurs. It occurs at both places. So you don't need to worry about it. We're just going to compare the rest. Okay. Now, next question. How many words are there in the vocabulary? Open your eyes, count, and tell me. The vocabulary comes from the training set, folks, right? Always. How many words are there?
It's 27.
Be careful. Just read it. How many words are there in the vocabulary? I'm not talking about a count. We're defining the vocabulary. You understand the question? We're talking of vocabulary here. So the same word, if it occurs 5 times, does it add 5 words to the vocabulary? No, it doesn't, right? It adds only 1 word to the vocabulary. So just figure out the distinct number of words in the vocabulary. How many are there?
19?
Sorry?
Is it 19?
19 or 20? Just check. Let's do this.
It's 20.
20, right? So
Yes.
just plain boring, entirely predictable and lacks energy. No surprises and doesn't come again. Very few laughs. Very doesn't come again. So we skip it. Powerful. Then we have the most fun film of. We skip the again because we've already included the summer. So that's 20. Okay. So the number of words in the vocabulary is 20. Okay. And as we discussed, we're going to skip 1 word, which is with, because it doesn't figure in the vocabulary at all. All right. Now let's try to figure out the probability of predictable given negative sentiment. All right. Now remember, folks, we are going to use Laplace smoothing. So first things first. So let's go back to that Excel just to understand. So what do we do? Okay, we're talking of negative sentiment, right? Okay, let's say some negative sentiment. Figure out the words, their count, get the total number of words. Of course, this does not assume Laplace smoothing. So what did we do? To do Laplace smoothing, we added one word each from the vocabulary to each class. Correct? Let's understand. That's what we did. We added one word each from the vocabulary to each class, and then we determined the probability. Okay. Now, so before we proceed, sorry. We need to determine the probability of predictable given negative class. Okay, that's what we're going to figure out. Now here, okay, forget Laplace smoothing. Let's say there's no Laplace smoothing, okay, for the time being. What would be the probability of predictable given negative class? How many occurrences of predictable are there in negative class?
1.
Sorry?
There's 1 occurrence.
1 occurrence. And then how many words are there in predictable class? Now just question, when you calculate the total number of words in the predictable class, if the same word occurs, say 5 times, would you count it as 5 or would you count it as 1? Remember, while figuring out the vocabulary, we counted it as 1. My question is, if the same word occurs multiple times, would, for example, unfortunately, there is nothing such, there's no such word here, right? I don't find anything except we have something in the positive class, but we don't have anything in the
And is there.
negative. I think everything, and is there, right? Okay. So my question is, if the same word occurs multiple times, would you count it as 1 or would you take the entire count? What is your take on that? I'm not talking about vocabulary. Sorry.
We'll
Closer.
consider the entire count.
Exactly. You would consider the entire count. Why? Because it's like saying, I have a bunch of negative documents. I keep saying it sucks, it sucks, it sucks 5 times. So which means the word sucks is very, very closely associated with negative sentiment, because the bunch of negative documents uses that word very, very frequently. Correct? Otherwise, what is the difference between one word and another word? There's no difference at all. Right? So higher the count, higher the more the impact of that word in carrying that sentiment. Right? So my question is, forget Laplace smoothing. Let's say there's no Laplace smoothing. Then tell me in fractional terms, what is the probability of predictable given negative class? How many words are there? How many words are there in negative class? Count, of course. How many are there? Sorry, was it Sandhya? You were answering, right?
I guess I'm wrong, VC.
But what was your answer? Maybe you're right. 1 by?
1 by 3.
Why 1 by 3?
I assumed the total number of classes, total number of negative classes.
No, you mean total number of negative documents, right?
Yes, VC.
No, look at this. How did we figure out, take this probability of exhilarating given positive? How did we figure this out?
4 by 7.
Okay, so what did we do? We took the number of occurrences
Number
of the word divided by the total number of words, right? Correct? In that class. So now tell me. Probability
1 by
of
14.
1 by 14. That's right. Why? Because there are 14 words. There are 14 words in the negative class. You see that? Just plain. Not, when I say 14 words, I'm including the same occurrence of the. I'm counting the same occurrence of words, right? I'm not counting them as 1. Okay. So in this case, very occurs 2 times. And if it occurs 2 times, I'm counting it as 2. So effectively, what you have to do is just count the whole thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 words, right? So probability of predictable given negative class, if I'm not using Laplace smoothing, is 1 by 14. Okay. Now I'm going to use Laplace smoothing now because it's safe to use Laplace smoothing. Now, if I use Laplace smoothing, what will happen?
It will become 2 by 34
Why?
because we have to add 1 to that, predictable, and we will divide it by adding the total number of vocabulary, which is actually 20.
Exactly. So the way it will work is, you see this, folks? Any word, when you apply Laplace smoothing, what happens? Any word prior to the Laplace smoothing, the frequency will increase by 1, isn't it? You see, love, which was 3, becomes 4. Exhilarating, which was 4, becomes 5. There were a bunch of words that never existed. We just added 1. So it's like saying, look, sucks was 0, now sucks is 1. Horrible was 0, now horrible is 1. All right. And then in the denominator, remember the total number of words, it increases by the count of the vocabulary. So in this case, the vocabulary is, we had 20 words in the vocabulary, right? In the example that we were working with. Of course, in this case, the number of words in the vocabulary was 4. So which is why the total number of words becomes 11. So that's basically 7 plus 4. All right. So you can use a similar argument. So prior to the Laplace smoothing, this was 1 by 14. There were 20 words in the vocabulary, right? So after Laplace smoothing, it will be 2 by 34. Okay. Now, let's do this so that, we kind of get the idea wired into our brains. So let's do probability of no given negative. Let's do it without Laplace smoothing first. No given negative. Without Laplace smoothing. Simple, folks. You already figured out negative. You know how number of words, negative words, the count.
1 by 14.
1 by 14. Simple, right? One occurrence of the word no. 14 words in the negative class. Not when I say 14 words, again, the same word is, occurs 5 times. I take it as 5. Okay. 1 by 14. After Laplace smoothing, how many?
2 by 34.
2 by 34. Exactly. Same funda. Add 1 to the numerator, add 20 to the denominator. Okay. Third, probability of fun given negative.
0.
Exactly. 0 by 14, effectively. Correct? There's no occurrence of fun. So this is where Laplace smoothing will be useful now. With Laplace smoothing,
1 by 14. Sorry, 1 by 20. 1 by 34.
1 by 34. Exactly. Correct? So without Laplace smoothing, it was 0 by 14. With Laplace smoothing, it will be 0 plus 1 by 14 plus 20, 34. Okay. And let's do this as well. Probability of predictable given positive. Let's do it without Laplace smoothing.
0. It is 0, right?
Sorry?
It is 0, right?
No, but give me the fraction because we're going to do Laplace smoothing as well, right? It is 0, but give me the fraction. 0 by?
8.
9.
Count it. Remember, this is not vocabulary. It's a total count of words. Is it 8 or 9?
9.
9,
9.
right? Because remember, vocabulary, when we figure out the vocabulary, if the same word occurs 10 times, we take only, the count is only 1. But here we're not doing that. Okay. The frequency matters. So it is 0/9. Now tell me, if I apply Laplace smoothing, what is the probability?
1/29.
1/29.
29.
Sabari, did you get the same number?
Yes, please.
All right. Okay. Next, probability of no given positive. Apply again before Laplace smoothing.
0/9.
0/9. And then apply Laplace smoothing.
1/29.
1/29. Probability of fun given positive. Before Laplace smoothing.
1/9.
1/9.
9.
1/9. After Laplace smoothing.
2/29.
2/29. Absolutely. Okay. Now you have every single piece that is needed for you to do that calculation. Okay. I don't want you to do that calculation, but I'll show you what. Give me a moment. I'll show you the numbers so that. Give me a sec. Sorry, give me a sec, folks. Let me just Google it up from where I picked the problem. Okay. Here we go. So you're right, folks. 2/34, 2/34, 1/34, 1/29, 1/29, 1/29. You basically multiply, and then this is the probabilities. And I mean, the one which is greater is the class to which you assign that document. Okay. There is just one particular aspect that I wish to discuss. So let us say there are, I'm going to ask this question. Let us say there are 10 features, okay? F1 all the way up to, say, not 10, let's say 100 features, okay? Now the probability of, say, feature 1 is 0.01, this is 0.0, each one of them is 0.01, okay? Let me just drag it, wait. Okay. Now what are we going to do? We're going to multiply. We're going to multiply these probabilities, right? Let's say this is all F1 given. Let's say this is F1 given some C1, F2 given C1, F3 given C1. Sorry. And as I said, there are 100 features. Given C1. What do you think will happen when I multiply these numbers? Any idea? Okay, by the way, you know what? You know the math. Tell me, what is this number? What is the product of all this?
Ten power minus 200.
Correct. 10 to the power of minus 200. How did you calculate?
Like 10 power minus 2, 0.01. So it is multiplied 100 times. So in power 100.
Correct. Exactly. 10 to the power of minus 200. Class 8 mathematics. Now let's say I do this product. Let me see what I get here. Sorry. Okay. In this case, it worked. But sometimes what will happen is you will face a problem where the programming language may not be able to compute the number. Okay. It's because the number could be very, very small and the programming language may fail to, it's called a floating point error or something like that. Okay. It happens when you deal with very, very small numbers. Now, what is the alternative to this? That is what I'm saying is when you calculate, let me just see if they brought this issue up here. Give me a moment. No, they haven't brought this issue up here. Give me a sec. They just mentioned this to avoid underflow effect. I'll tell you what it means. Basically, there is a possibility where when you work with very small numbers, your programming language may not be able to compute. It may not be able to multiply and then compute, you know, I'll give an example. So let's say there's 100 factorial. And then there's a 99 factorial. Okay. And I'm dividing these two. Can you tell me 100 factorial by 99 factorial? What is it equal to?
100.
100, correct. But interestingly, you never calculated 100 factorial. You didn't calculate 99 factorial, did you? You did. But if a programming language were to do it, or if Excel were to do it, what would it do? It will calculate 100 factorial. So for example, this is what it's going to do, right? And then it's going to divide these two. Luckily, this works. But let's say this is 10,000, or let's say something like this. And then this number is you see what has happened? Excel has gone crazy. If this number were to be 10,000, or let's say even 1,000, let's say what happens if it's 1,000? Even 1,000 doesn't work. You see, Excel goes for a toss. Even though, if you look at this number, you know that factorial of 1,000 divided by factorial of 999 is equal to what?
1,000.
1,000, correct? We know that because we're doing the math using pencil and paper. So we know. So we do the cancellation and then we know it's 1,000. But Excel doesn't know, and programming languages don't do it. So you will face a similar problem with this. When you multiply these small numbers, in this case, it worked out. But if it's a very, very small number and if there are a lot of features, I mean, just imagine the English language. and look at imagine the vocabulary, folks. So if English language has 40,000 words, then in practical scenario, your vocabulary that you're dealing with 40,000 words. So you'll be dividing it by a 40,000 number. You'll see a 1 by 40,000 many times coming up. So the number, the probabilities could be very, very small. So when you multiply them, it can go crazy. So how do you solve this? How do you solve this? So basically you have numbers A, B, C, D, very, very small. I can't deal with this. I mean, no, let's say computer program can't deal with this. So how do we ensure that the computer program is able to compute this? Any ideas?
Log.
Log, exactly. Brilliant, right? Why? Because we know log of AB is equal to what? What is log of AB, folks?
Log of A plus log of B.
Exactly, log of A plus log of B. So what have we done here? We have basically converted something that is multiplicative to additive, right? So if you take this case, let's say I calculated to base 10. So here we go. I made it simple now, you see? Now I can easily sum this up. And then how do I get to the product? I'll have to take the anti-log, correct? Right? So basically you do this, and if I have to get to AB, I'll calculate the anti-log to get to AB, right? So, which is why you would see many of these expressions are in log terms. So even here, what we are doing is, in practice, they convert this into log terms so that you can easily calculate that expression. You'll find that here. For example, you see the log of whatever, all right? Largely for, I mean, it's easier. Anything that's multiplicative becomes additive, so life is easy when you work with logs, all right? Any questions? We have a hard stop in a short while, but any questions?
We see when you're building a model, you don't give all these formulas, right? You basically use some libraries, or do you give these formulas?
Of course not.
So all the libraries will have it in log format only.
Internally, yes, they should, correct? Otherwise, the libraries will fail, isn't it? Right? See, now you're right. The thing is, we are doing all this because, again, the model, I mean, the libraries will have a lot of parameters, correct? So unless you know how the model works, you wouldn't know what parameter to pass, what value to pass. Which is why we're doing this stuff in depth. But of course, as you rightly pointed out, you would have standard libraries to handle all this. And I believe it must be using log function. Otherwise, there's no way the programming language could handle this. Any other question, folks?
We see in the example which we were, I mean the one which you had in the Excel, where you showed the Laplace after adding Laplace. So here, right, we have ignored a few words, right?
Correct.
But in the one which we were calculating now recently, in that we did not ignore.
No, we did. We ignored the word with.
Okay.
This word with was ignored. So even in terms of, if you look at the document here, this is what they say. So what do we do about words that occur in our test data but not in our vocabulary? Because they did not occur in any other training document. The solution for such unknown words is to ignore them.
Okay. Yeah.
All right.
VC, I do have a question.
Go ahead.
So in the given example, we have classified into two classes, right? So
Mhm.
it's positive and negative. Okay.
Correct.
So we are calculating the probability of positive given the document as well as probability of negative given the document. Okay.
Correct.
So whichever is higher, we are assigning to that particular class, right?
Correct. Correct.
Now, if these two have 50% probability, so here we cannot assign to positive or the negative class. So in this scenario, we will make will it become like determinable or something like that?
Not necessarily. You can assign it to any class then, right? It doesn't really matter then, right? But just
Okay, so we
imagine
have a
when you're dealing with such probabilities, the probability of such a thing to happen is very, very minimal, isn't it? Just imagine. In
yes,
practice,
please.
theoretically it can happen. But what is the probability of such a thing to happen in practice? Given that you're dealing with 0.01, 0.009, that sort of numbers, and you multiply them, what is the chance that two of them will become equal? It's very, very minuscule, isn't it?
Yeah,
Don't you
right.
think so? You
Yes,
can
yes, yes,
manufacture
VC.
a scenario to make it equal, but in practice, it'll rarely happen, if at all.
Okay, VC. So, so we can assign to any class. So, for
Yeah, of
example, if
course,
we are
of
coding,
course,
if you are okay, got it.
right? And,
Right, VC.
and this is, of course, what we've done here is basically a binary classification. There can be what is called as a multinomial classification, where you can assign a document to multiple classes too. We have, of course, looked at the trivial case of assigning it to 2 classes, but then there can be 5 classes. For example, positive, negative, indifferent. People are indifferent about movies, right? They don't know whether it's positive or negative, right? So they'll use words like maybe, not too bad, that sort of thing. So that can also be another class. Of course, we trivialized it. We kept it simple by having only 2 classes.
Okay, we got it.
Anything else? All right. If there is nothing else, thank you, folks, for joining this call on a Friday evening. Catch you on Monday. Cheers.
Thank you.